In this video, I'll introduce you to the problem that we'll be working on solving over the next couple videos. I'll define what's meant by distinct labelings, and we'll look at some examples. So the goal here, Prufer codes, the goal here in this first part of the section is to determine a formula for the number of distinct labeled trees of a given order, n, using the labels 1 through n, those integers. Now, as I mentioned before, there's no known closed form formula for the number of graphs of any given order, and there's also no known formula that's closed form for the number of trees of a given order. That's also a very difficult and intractable problem. However, if we consider labeled trees instead of just unlabeled trees, there is a known formula for it. And that's what we're going to be working on in these videos. So the first thing I need to mention is what is meant by distinct labeled trees. So first off, two labelings of the same graph and using the same set of labels. Two labelings are considered distinct if they result in different edge sets. So here I have an example of 3 labeled graphs of order 9. And 2 of these are actually the same labeling. And so this actually accounts for 2 distinct labelings of this graph. So, right, we say 2 labelings are distinct if they result in different edge sets. So what we need to look for here to determine if 2 labelings are distinct is the resulting edge sets. So maybe I'll try and list the edge sets here. So the edge set here would involve the elements, let's see, we have 1 and 2 are adjacent, so 1, 2, we have 2, 3, we have 3, 5, we have 5, 4, we have 5, 6, 6, 8, 8, 7, 8, 9, and 2, 9 would be my edge sets, for this first graph. Now here I'm just listing the edges just by sticking together the vertex labels. So these aren't to be interpreted as 2-digit numbers, but rather 2 single-digit numbers that are juxtaposed. So that would be this first graph. And if I take a look at the second graph, let's look at its edge set. 1, 2. I'll start over here at the vertex 1. I have 1, 2. I have 2, 3. I have 3, 5. 4, 5. 5, 6. 6, 8. 8, 7. 8, 9. And 2, 9. And if you'll notice, the edge set in the second graph is exactly the same as the edge set in the first graph. So these 2 labelings are the same. This is the same labeling. Now, if we take a look at this third graph, let me zoom out a little bit here. Let's find its edge set. So let's see, we have 1, 2, 2, 3, 3, 5, 4, 5, 5, 9, 8, 9, 7, 8, 8, 6, and finally 2, 6. So notice a couple things in particular, that this has the edge 2, 6 in it, while none of the other edge sets have 2, 6 in them. And so just there we can see that these are not the same labeling. So while these 2 are the same, this one is distinct from the other 2. Distinct from the other labeling. So this is what we mean by distinct. You can always just look at their edge sets and determine if the sets are the same or not. So we turn our attention back to the goal. Now that we understand what distinct labeled graphs are, here we're going to be looking at distinct labeled trees of a given order. Let's look at some examples. So here I have n equal to 3 in this row, and yes, I did just copy this page from the text. N equals 3. If I think of unlabeled trees on 3 vertices, that would just be P3 is the only labeled tree on 3 vertices. But as we can see here, there's 3 different labelings of this. So we can look at the edge sets for each one of these and verify that they're different than any of the other ones. And so there are 3, so number of distinct labelings. There's 3. And then here we have n equals 4 is the rest of this image. Notice with n equals 4, there are 2 unlabeled trees of order 4. That would be the star, K13, and the path, P4. So there's 2 unlabeled and number of distinct labelings. Well, here we have 4 different ways to label the star, K13. And then what do we have here? We have 12 ways to label the path, P4. And so there's a total of 12 distinct labelings of labeled of trees of order 4. So the general formula here, I'm going to give it away here. The general formula for just a given order n, the number of distinct labeled trees is n to the n minus 2. And in the next few videos, we are going to work on solving this. The idea is we're going to, by the way, this result was first proved by Cayley. I mentioned we would encounter Cayley again. And Cayley again is famous from algebra in particular, and was working with. This is why I was working with graphs, was because of chemistry. But the result we're going to look at is actually, well, it's Cayley's result. It was proven by this guy Prufer. So that's the proof we're going to look at, is Prufer's proof. What a great name for a mathematician is Prufer. So the proof is going to involve 2 algorithms. One for taking a labeled tree and producing a list of n minus 2 of its labels. And then the other algorithm is going to be taking a list of n minus 2 n minus 2 labels and producing a given labeled tree from this. And so the idea is those 2 algorithms are going to establish a one-to-one correspondence. So how are we going to prove this? How will we prove? We're going to establish a one-to-one, or I guess I'll say a bijective correspondence between the labeled trees of a given order and the sequences of length n minus 2 from a set 1, 2 up through n. Given order n using the labels 1, 2 up through n. And then since there are, so here we're number of sequences of length n minus 2 from this set, we're allowing repetition. So the number of sequences of length n minus 2 will be n to the n minus 2. Right, we have n minus 2 to choose from a set of size n. We're allowing repetition, so that's n to the n minus 2. And once we establish this correspondence, the same will be true for these distinct labeled trees. Okay, that's the idea. In the next couple videos, we're going to look at these two algorithms that are going to help us establish this correspondence. And then in the final video of this 4-part video series, we'll prove this result. See you there.